Geologic time. This is the geologic time scale. The Earth is roughly 4.55 billion years old, and just like we break up our year into months, weeks, days, minutes, and seconds, we break up geologic time into pieces so we can better understand it. The largest segment of geologic time is the eon, and it's here in this image on the left. Phanerozoic, Proterozoic, Archean, and Hadean are the major eons of geologic time. These are the largest segments. And if you notice on the right, we've got age in millions of years before the present. The oldest is on the bottom. So the oldest eon is the Hadean. The most recent eon is the Phanerozoic. Each eon is broken into eras. There are 3 eras. Paleozoic is the oldest, Mesozoic, and Cenozoic is the newest. We break eras into periods. Quaternary is our current period. Cambrian is the oldest period. And finally, we have epochs. These are subdivisions of periods. We are currently in the Holocene, which means human time. Previous time was the Pleistocene, which was the Ice Age, the most recent Ice Age. Each division of time is different from the others, not so much because they're equal breakdowns of time. If you look at the numbers here, there's no equality between each section. They are named for and divided by what life was most common at that time. Atmosphere, climate, and continents have all changed throughout geologic time. This is rather an interesting little image showing geologic time from way back 4.5 billion years ago, then when the solar system was first forming from a nebula cloud. And then there's a whole long wait, about 3 billion years ago, the earliest organic structures. 2 billion years ago, first cells. 1 billion years ago, multicellular. Precambrian, not much. And it's the last few turns of the wheel here that are the most common, where most of the life has happened. And it started from incredibly simple to far more complex. This is an image showing the true division of geologic time. Age is oldest is to the far right, the beginning of the Earth. And the majority of time is this section called the Precambrian. It's those first 3 eons. And it's basically that time when there's not much going on. And then you've got the more recent time that where most of the life has happened. Precambrian, 4.55 billion years ago to 0.57 billion years ago. MYA stands for millions of years ago. Precambrian is famous for the formation of the Earth. Our oxygen atmosphere forms. The original atmosphere was not breathable for us. It would have been highly poisonous, made mainly from volcanic belching, if you will. But by the end of the Cambrian, oxygen forms in our atmosphere. The life at this time is single-celled, algae, and worm-like organisms. Remaining rocks from this time are very bent and folded, highly metamorphosed, or broken down into sand long since, so it's rather hard to read. But there were several different glacial periods that we are aware of, so the climate changed dramatically throughout the Precambrian. About 4.5 billion years ago, this is what the Earth would have looked like, all molten. Volcanic outgassing releases carbon dioxide, water, and other gases, making an atmosphere, but there's little or no oxygen. Over billions of years, the Earth cools, rain falls, solidifies in lava, and bacteria, cyanobacteria, evolve, releasing oxygen into the air. This is what gave us the ability to have this type of life that we currently have today. Evidence for this are iron deposits from the Precambrian. Here, if you look here, it's very rusted. Before these deposits, there was no free oxygen. which means that there was no rust. We know that because before this time there is no red bands like this. It's just iron. It's only when you reach rocks of this age you suddenly start seeing rust, indicating that there was oxygen available to make the rust. This is oxidation, a form of chemical weathering. The Paleozoic means old life. Originally, if you talk about evolution, you start with some creature. Mutation, naturally occurring mutation, gives us several varieties. Some varieties don't survive long enough to produce offspring. Others do. They reproduce, some may mutate as well. Things that can't compete as well die out before they reproduce, and the more favorable things survive. So you go from one unique thing to stronger, more varieties. This is the key to evolution. Paleozoic is famous for the beginning of abundant life. Coal deposits. Most of our coal in Pennsylvania, Mississippi, West Virginia are all from the Paleozoic period. Ends with a major extinction before the dinosaurs and the formation of Pangea. Between the Paleozoic and the Mesozoic, nearly 95% of all species on Earth died out. It was a major extinction. Causes of this extinction include volcanism and climate change. There was extension of climate change by glaciation. It suddenly became much colder. Sea level dropped because there's more ice, so there's less aquatic environment available. And volcanic eruptions put sulfur and ash into the air, blocking sunlight. So these three things together are what helped kill 95% of life on the planet. Also in the Paleozoic, the Ordovician, first was a second section. North America was on the equator and had warm inland seas. Most of the place was covered in water. The Silurian, North America became very dry, left behind lots of salt. There are huge salt mines in New York, for instance, that were formed in the Silurian. In the Carboniferous, lots of freshwater swamps left coal deposits in the east, thus the term carbon. Carboniferous means lots of, so lots of carbon was formed at this time, coal. And in the Permian, it suddenly became very, very dry, and then an extreme ice age. The Paleozoic was known for the trilobites. These are the fossils most common in this segment of geologic time. It is also the age of fishes. We call it fishes, plural, because there were many different varieties of fish. Some had armor, some had spines, some had no armor or spines, some had no backbone at all. Very wide variety. Next we have the Mesozoic. Meso means middle, so middle life. Middle life is famous for dinosaurs. Ends with a major extinction of over half of all organisms, primarily on land, from meteorite impact. And Pangea starts to break up as well. Climate is very mild, very little glaciation. That's why, images of the picture Jurassic Park, that movie, was very jungle-like. That was very typical for the time period, actually. Forests were growing at the poles, and coral, like you see in the Bahamas, was growing up in Europe. So it's extremely warm. These are some common dinosaurs of the time period. After the extinction came the Cenozoic. Cenozoic means young life. This is famous for being the age of mammals. Without the large dinosaurs to contend with, mammals could grow and evolve to fill in the niches of the ecosystems that were remaining. Humans also evolve. Climate in the Tertiary was warm and humid, but then an ice age occurred, and this is the Great Ice Age you see in the movies. forests turned into grassland, which caused an incredible change in the animals of the time. And in the Quaternary, we cycle back and forth between warm and cold. We are in a warm period. Only a tenth of the area that used to be ice still is. The oldest hominid, Australopithecus, about 5 million years old. And this is the skull of it. Ape-like brains, human-like jaw, bipedal. Next came Homo habilis, 2 million years old. A larger brain, started to use the simple tools. And then Homo sapiens, only been around for 400,000 years. Larger brains, this includes us. We have the pronounced I ridge as well. So this is images depicting what might have looked like a typical one. Notice the brain becomes larger for a while, and then ours, rather, from comparing to Neanderthals to sapiens, ours is slightly more complex. Not larger, just more complex. Here's a key. Dinosaurs and humans did not coexist. Dinosaurs died out 67 million years ago, and humans have only been around 5 million years. So we never had to worry about T-Rex hunting us down from our caves. Now, how do we find these dates? To figure out actual ages, something called absolute dating. Relative dating is one thing in comparison to another. I'm older than you are, you're younger than I am. Absolute dating is giving a number for it. Actual numbers, like these on the side of the geologic time scale. Some evidence we gather through tree rings or ice cores. Here's images of coral growth bands, tree rings, and ice layers. First, scientists drill into the coral and extract a sample. They take an X-ray image of it. You can see the growth bands. Each one is a year, and that gives us an idea of how many years ago from the top, which the age we do know, back in time to an earlier growth line. And we can figure out from the thickness of it what sort of environment the area had, what climate it had. Again, here's another one. You can do the same with tree rings. And what we do is we take a more recent ring, a tree, and the rings are dependent on climate. So we lay out, this is from this tree, and then this one is from this tree. And we match it up so it lines up with the previous tree, the date we know, and can reach an earlier time. This one, used to build a house, gives us an even earlier time. So this gives us a longer period of time where we can get climatic data based on trees. We can even record forest fires like you see in this image. Finally, we use ice layers. So we drill for ice in Greenland or up down in Antarctica. These are some layers of ice from a core. The summer layers are the paler colors, and then these are the winter layers. So we have an idea of the year. We can figure out how much snow fell in a year. We can also look at bubbles inside the snow. The glacier, the ice was originally snow, and it trapped air inside. And we can analyze the gases in that air to figure out how much carbon dioxide was in the air, how much oxygen was in the air, and find out a great deal of information from these ice cores millions of years back. Those ice cores are also called varves. The final thing we do is analyze something called radioactive decay. Here we've got a radioactive element. It's unstable. And at a predictable rate, it will release radiation and decay, change into something else. The original radioactive element we call the parent, and what it changes into is called the daughter. Parent to daughter. And that happens over and over and over. Half-life is the time it takes for half the atoms in a sample to decay to something stable. For instance, here we have 100 kilos of a parent element, say it's uranium, and no daughter element. This is pure uranium-238. After one half-life, half of the parent will have been turned into daughter. So it will have a ratio of 1 to 1, 50 kilos of parent, 50 kilos of the daughter. After two half-lives, the 50 will be divided in half, and there will only be 25 kilos of the original parent, and 25 more have been added to the daughter. After three half-lives, there will only be half as much parent, 12.5 kilos, and the remainder, 87.5, will be of the daughter. And over and over and over, the half-lives will drop. So imagine the half-life of a particular parent element is 20 years. How old would a 100-gram rock containing only 20 gram of the parent element be? So 100 grams, we can even use this image at the top. 100 grams, just like 100 kilograms. If it only has 25 of the original 100 of the parent left, it must have been two half-lives. If the half-life is 20 years, it must have been 40 years. So two half-lives to leave you with from 100 to 25, and if a half-life is 20 years, then it has been 40 years. If the half-life of that same rock is 100 years, two half-lives would be 200 years. This is how we figure out the age of rocks. Here's a graph of it. Originally, you start with one quantity of parent. After one half-life, half as much will be left. Two half-lives, a quarter. Three half-lives, an eighth. Four half-lives, a 16th, and so forth. The parent element will decrease, 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 almost getting to zero, just getting too small to measure. And the daughter element will increase, increase, increase until it almost seems like pure daughter. Here's an old, silly cartoon. When I was young, I used to feel so alive and dangerous. Would you believe I started out life as uranium-238? Then one day I accidentally ejected an alpha particle. That's radiation. Now look at me, a spent old atom of lead-206. Seems that all my life since then has been nothing but decay, decay, decay. Alright, here are the isotopes we use for radiometric dating. You've undoubtedly heard of carbon-14 dating. That is the most important one, and it's the one that you're going to need to remember for the test most strongly. Carbon-14 decays into nitrogen-14. Its half-life is 5,730 years. So that means it's effective dating anything from 1 century to 70,000 years. And it only works on things that were once living. So this is why we use carbon dating most frequently in archaeology, studying human history, because that's fairly short. Uranium-238 decays to lead. It has a half-life of 4.5 billion years. So it's only good on rocks that are older than 10 million years old that contain uranium. Things like zircon, zirconia crystals, are often found in some of the older rocks, and so we are good at dating them that way. We also have rubidium and potassium. Both of these are good for specific time periods and specific types of rocks.